I forgot to start recording, but it's all right. One problem. Okay, what else we got? Yes,
On that same exam, you do question 5.
yes. Question 5, same exam. Suppose, okay, so I'll read the question and we'll try to force on it. Suppose G is a group and N is normal in G and the index is P squared. Show there must exist a subgroup H of G with the index P. Okay, so here's the setup. N is a normal subgroup P such that show there must exist a subgroup. There exists a subgroup. H of G containing N that is, I can find some sort of H lies between this N and G such that the index. So think of it this way. N is small compared to G. It's got P squared cosets. Show you can find some group that's a little bit bigger than N that's not quite as big as G, so it's only got P cosets. Right? By the way, this business here with N with H lying between N and G, does that sound familiar vaguely? It sounds like the third isomorphism theorem, doesn't it? Right? The correspondence. Let me ask you this. One of the things that pops up here is this fact that it is normal in G. What's the significance of that? What's one of the big things about normal subgroups? What's cool about them? Right, but in terms of quotients, I get the forms a group. So since N is normal in G, then G mod N is a group. And so by group, because the order of that group is the number of left cosets, which is that index P squared, right? Let me ask you a question. What does Cauchy's theorem tell us about any group of order P squared? I agree with that. Cauchy's theorem said that if you have a group of order N, if P is any prime that divides N, there has to be an element or a subgroup of that order, right?
That P is like if very.
Oh yeah, I hope I said that problem.
You don't mention it.
I certainly did not say that problem. I can only assume that I told my poor hapless students that he was prime during a test. Got to correct it. So, but yes, I do need P to be prime. Otherwise, the problem's not true. If P was 6, this doesn't work in general. Thank you for pointing that out. I'll try to remember to fix that. Yeah, P must be prime here. So here's a group of order P squared. It has to have a subgroup of order P, right? P mod N has a subgroup of order P. And this is by Cauchy. Because it has to have, as you pointed out, an element order P, and that element order P will generate a little subgroup order. Everybody cool with that? And the third isomorphism tells us that um, uh, this subgroup of G mod is of the form H mod with H squeezed in between K. I'm sorry, the K, yeah. And K. Right? So what we have is the order of H mod n is equal to P. We know this group exists by Cauchy. We know it takes this form of third isomorphism. So that means that means the index of n and h is P. That's the number of left cosets in H. We also know that P squared G colon n. And how can I break that down?
Because the index of H would be.
And we know that this is P. So what I get is squared equals so the index has its side. Everybody okay? Yes,
This isn't a problem. This is just like where I guess I'm having a little bit of trouble wrapping my head around the third isomorphism theorem. I guess because it's a lot at once.
okay, so
But I
let's,
don't know. That's not a specific question. I'm sorry. I don't know.
well, let me give it, that's fine, that's fine. So let's look at, actually, let me take a step further, an example I sort of started here. This is what the third isomorphism says. For example, if I have and then I have what the third isomorphism theorem says, or one of the things it says, is there's a one-to-one correspondence between any group you find here, H, and subgroups of G mod n, right? In this case, and let's see if we can see how the correspondence works. In this case,
So H is the one-to-one correspondence.
what's that now?
H is the one-to-one correspondence.
What is one?
I'm confused with why H.
H is an intermediate group, and every intermediate group you find between here and here.
Okay.
You can realize that you can have correspond to a subgroup of this quotient.
Okay.
Which is E12. Now, let me list the subgroups. This, the biggest one, let's see, look at this. All exhausted, 0 bar, 1 bar, 2 bar. Now, and of course, you have the small guy, which is 0 bar. Remember, this is a cyclic group, so there's one and only one subgroup for every divisor. This is the big one, who's got 12. This is the little one, who's got 1. What are my other divisors? Well, 6 is the divisor. So I've got something that looks like, here's a subgroup here. 4, 6. That's the subgroup of this consisting only of even things. And you can see that, and here my addition is mod 12 again. 6 plus 8 is 14, which is 2. 4 plus 4 is 8, which is in there. 8 plus 8 is 16, which is 4. This is a subgroup of order 6. Let's see, what are the other divisors? 4. There should be a subgroup of order 4. If you might pick that one out.
Here.
Good. 0, 3, 6, 9. That has 4. So it's every third step. So what do we got here? 12, 6, 4. There should be a 3 and a 2, right? Subgroup of order 3, I guess would be 0, 4, 5. And 1 order 2.
The side with, are all the subgroups of, Z12 also the form DZ? Like DZ12? Where B is a integer
All subgroups of what?
of Z12 or Z mod.
Yeah, it would have to be a multiple. Well, yeah. If it's a subgroup, see, are you talking about 12 C or you talking about Z12?
I'm talking about Z12.
Yes, all subgroups are cyclic, so they're generated by a single element. So all you gotta do is take that element and see what it generates, right? One will generate everything, and in fact, everything that's relative from prime to 12 will generate like 7. But it goes kind of funny where it goes 7 and 7 is 2, and 9, and then 4, 11. So this is a size 12. This is isomorphic. C6. Because it's cyclic for 6 elements, right? This is isomorphic to C4. This is isomorphic C2. And this is isomorphic C3. And I drew them that way because the containments are kind of funny. So of course, this one contains all. But notice you have this kind of pattern like this. Oh, and also like that. All right. So 0 is contained in everything. This is contained in this, which is contained in this. 0, this subgroup of order 2 is kind of interesting because it's contained in the subgroup of order 6 and 1 order 4 as well. So that's the way the containments work. Now, basically, what the third isomorphism theorem says is these subgroups here of Z12 should correspond to these intermediate groups here. And I'll show you where the pattern works. 0 corresponds to, see, I like this color. So the correspondence works like this. One subgroup of Z that contains this is 12Z. 12Z mod 12Z is 0. So this corresponds to 12Z. What does this one correspond to? This one corresponds to the subgroup of Z that's Z itself. Because Z mod 12Z gives you this. How about this? You want to take a shot at this? This one? The other way, 2Z. This corresponds to 2Z. Because 2Z mod 12Z, you should have 6 elements, right? 2 is the generator, 4, 8, 10, and like that, right? What does this one correspond to? 3Z mod 12Z is, see, I have to think about it, but yeah, that's right. It's corresponds to 3Z. This one, I guess would be 4Z, right? And what else we got? This one, 6Z. And in fact, you can look at the generators, you have to tell what it is that's governed this. You see, that's what that correspondence theorem says, is if you have a subgroup here, call it H, then H mod N has to correspond over here. And if you have a subgroup over here, it has to correspond to an intermediate group that's between N and G here. And the way the correspondence works is you take H mod N, which is exactly what we did here. When you take Z, the Z mod 12, you get the big guy. When you get, say, 2Z mod 12Z, that means your 2 is your generator, and at 12, you go back to the identity, so you get the subgroup 4 of 6. Yes.
Isn't that also isomorphic to C1? The last two, the theorem.
Yeah, Z mod 1Z, yeah, that's right. Because here, this is kind of a degenerate case because you've only got here. Are you okay? Okay, others. It's
Absolutely. Another example of theorem 2.2.1, which is like if F is a finite field with Q is key to the N element, then the group of non-zero, the group of n by n matrices with non-zero determinants equals like Q to the N minus 1 to the N minus 2.
oh yeah, that's kind of a counting movement, and we did that for like the. See, so find number okay, so this was back to that. Let F the with Q. How many n by n diagonal matrices are this is, I think, easier than the problem that you were about, but I think this might be easier. So the question is, what if you have to fill some number of elements in? We'll just allocate. How many n by n vertical diagonal matrices are there? Right, there are. But Well, what does an invertible diagonal matrix look like? Well, it's got zeros in the words, it's diagonal. So they're a diagonal entry. Okay. Now, what do you know about diagonal entries? Can't be zero. So how many choices from slam do we have? You can pick any element of the field, it's not zero. So how many of these matrices are there? Q minus one B. And this actually forms a group, doesn't it? Right? Because what happens if I take two diagonal matrices, these form a multiple? What do you get? Another diagonal matrix, and if none of the entries on the diagonal are zero, then the product has no zero entries on the diagonal, so it remains vertical, right? So this is actually a group. What's different about this one as opposed to a lot of the other matrices? If you look at the n by n diagonal matrices, rephrase n by n invertible diagonal matrices, then that'll be an abelian, right? Because since the matrices are all diagonal, it doesn't matter. I'll give you another example. This maybe I've used somewhat. Somebody brought this up before, so I'm gonna call it Z2. Z2, I've only paid attention to them to adding Z2, right? 1 plus 1 is 0, 1 plus 0 is 1, and so on. But it's actually a field because what does it mean to be a field? Well, Z2 under addition is an abelian group, right? The easiest one I can think of, but except the academic, right? And if you throw out 0, all you've got is 1. And that certainly is a group under multiplication, right? So this is actually a field. It's like the easiest field that I can think of. Now, what's one of the first places where you started spreading out in vector spaces was probably, even if it wasn't Cauchy this way, when you did it, was probably in Calc 3 when you started doing functions of two variables, right? You did all these surfaces and so forth. And where do you live now? You live in R2. Well, let's live in Z2, 2 copies of it. And I'm liking that a lot better in R2 because there's a lot less interest. This is the set of things that look like A, B, where A and B are in Z2. This is actually a vector space over Z2. Right? And don't worry, I haven't completely, might think I'm up here having a stroke and maybe an amp, but there's actually a point that I'm looking like proof there. This is a two-dimensional vector space of Z2, right? Because when I add 2 of these things, and I add component by component, right? So AB plus CD is, this is math, so we did the easy thing. So the sum of 2 vectors is still a vector because both of these entries are in Z2. The 0 vector is 0, 0. And scalar multiplication is terribly easy because you can either multiply by 0, in which case it kills the vector, or you multiply by 1 and it leaves it alone. Everybody agree with that? So I would like all the linear transformations of this two-dimensional vector space of Z2. There's only 4 things there. 4 things. I would like to look at all the linear transformations that are one-to-one and onto, right? Remember how sometimes you had linear transformations that had a kernel, right? Null space and all that. I want invertible transformations. This, I'll call this GL two Z2. I want a list of all the 2x2 invertible matrices. Those are all linear transformations of this C2 cross C2, right? How can I make the invertible matrices? And this came up probably in that counting argument that you were first asking. Think about building a matrix row by row. I'm gonna be very organized. I'm gonna start with the top row. Now, the top row is a vector, right? So I've got four possibilities that I can put in the top row. But there's one thing I can't put in there. What's that? I can't put in 0, 0. Why? It wouldn't be invertible, right? And that's so I can put in anything except 0, 0. So let me start off by doing this. How about 1, 0? Now, what can I put down here and guarantee that the determinant is not 0? Well, right, what did you say, 0, 0, 1? Well, that's the identity. How about that? I can do that. But was that the only thing I could do?
Yeah.
Ooh, I don't know. Oh, my. Right. The key is to make sure that the determinant's not 0. All I got to do is put in something in the second row that's not linearly dependent with the first row, right? So all I have to do in the second row is just avoid a multiple of the first row. And the only multiples of that first row is the 0 row and that row itself. So as long as there's two other things I can put in and I'll do them both. And I can go through this pattern. I could do 0, 1, I can go 1, 0, or 1, 1. And I could have top row. And 0, 1, 1, 0, 1. And that's it. That's the exhaustive list.
But I thought this, like, if the diagonal.
What's that?
I thought if it was in the diagonal,
If it was in the diagonal, what?
like, if the entry was in the diagonal, it can't be screwed. Oh, wait, no.
Yeah, because don't forget these other ones. This is a group. Because these matrices are all invertible, right? So I know what the inverse of this is. Right? Can I come with the inverse of what's the inverse of this one? Self. What about this one? Right here. What's the inverse of that? Looks like itself as well. How about this one? Well, actually, how about this one? See the inverse of this one. Self. And I bet very hard that these two are inverse. And take on. You know what this group is? It says this group is isomorphic. There's the identity. Here are the 3, 2 cycles, and here is 1, 2, 3, and 1, 3, 2. In fact, let's look at this one right here. I've already sort of seen that these two are inverse of each other. What happens if I take 0, 1, 1, 1, and square it? This is 0, 1, 1, 1, 0, 1, 1, 1. And this is 1, 1, 1, 0. Right, which is the other one. And so 0, 1, 1, 1, Q is the square times 0, 1, 1, 1. So these two elements right here correspond to the 3 cycles. Matrices are very actually In your CI, they've been talking about representations. That's what sometimes people like to take an abstract group and associate it to a group of matrices because it's computation. Do things. But this is kind of a good thing. Matrix group. So this is S3 disguised. Any questions on that? Okay, other questions?
What it would be like a question that the second isomorphism. Like what like the idea of it?
There are some problems in group theory. I mean, I often I think of the second isomorphism theorem as accounting. Okay. In fact, I myself, I'm not saying that you have to, but I use the second isomorphism theorem actually in a homework problem that you asked. The one where you have a normal group and a subgroup H, and the index of the normal group controls the property of H. Second isomorphism is because those cosets, or because Hn mod n is isomorphic to H mod H intersect n, that actually helps you use counting. So it's useful. And I've used it actually for other things. And the first isomorphism theorem, well, that's the nuclear one. Right. And that's right, because one can consider the second and third isomorphism theorems as sort of important spin-offs of first isomorphism theorem, right? They're important too, right? I mean, Breaking Bad, great, but so is Better Call Saul's. Okay, other questions?
Review Cauchy's.
In Cauchy's theorem?
Yeah.
Okay, so. Cauchy's theorem says. So Cauchy's theorem, basically it says this, if you have a group and the order of the group is n, you have a prime that divides n, then there has to be an element of that order, right? Now, I did tell you something that you're not really responsible for yet, and that is if a prime power divides the order group and there's a subgroup, not necessarily an element of that order, but there's a subgroup of that order. We're going to get to that later. That's what the CELO theory is. But for example,
So that means that subgroup isn't generated by a specific element.
what's it now?
So then that subgroup isn't generated by one element, it might be generated by multiple elements.
So let me give you, here's an example. Then there exists an element of order 2 and that's the content of Cauchy's, right? Those are the only content about it. Now, let me point out that there are two elements in S three of order six. Because the element of order three, its inverse also has order three, right? There are actually three elements of order two, right, that are all sorted. So in this group here, Cauchy's theorem says that there is one, it doesn't say it's unique, right? And there are three different elements of order two that all generate different subgroups, right? So for example, all right, so, right. There is a group. It's called monster. It's not the biggest group ever, but it's, well, I'll tell you what that is. The order of them is 226 times 3 to the 20 times 5 to the 9 76 times 11 squared times 13 cubed times 17 times 19 times 40 times 20 times 29 times 31 times 41 times 47 times 59 times 71. Here's what Cauchy's theorem tells me, period. There is in the monster an element of 1, 2, 3, 5, 7, 11, 13, 17, 31, 41, 47, 7. It tells us no more. I just know that it exists some element of each of those problems. That's it. All right. Now, we're going to get later the zero theorem that will tell us in the monster there are groups, there are subgroups of order two. Subgroup of order two is generated by order two, that's where they come from. But there's also a subgroup of order 2 squared, 2 cubed, 2 fourth, 2 fifth, all the way up to 2 to the 46. So there's an enormous number of those. Same thing, ascending powers 3. Is there a subgroup of order 2 to the 23 times 5 to the 7? No idea. I don't know. Maybe there is, maybe there isn't. This group, by the way, physicists are fascinated with this group as well. So the history behind the monster is this. Can somebody remind me what a simple group is? Maybe I did. Maybe I did. A simple group is a group. Okay, so tell me two normal subgroups any group has. The identity in itself, exactly. If that's it, then the group is called simple, right? So a simple group is one who only, it might have many subgroups, but the only normal ones are the trivial ones, the whole group of the identity, right? Can anybody give me an example of a simple group that is abelian? Good, that's right. I like that's an easy ripoff, right? Can you generalize your answer? Z what? ZP. ZP. That is correct. If you have Z mod P, its only normal subgroups are itself. Now, the reason that works is this. If P is prime, then the group is cyclic, right? So the only subgroups are of order 1 and P. So by cheating, we sort of get that it's a group. Those are actually the only abelian simple groups. You're probably a little bit hard pressed to find another Because the smallest non-abelian simple group has 60 elements. And then the next smallest one has. The next smallest one, I think, has 168, right? But simple groups are sort of the building blocks of other groups. We haven't got, this is just for fun. Simple groups are building blocks of others. So there was this big classification of finite simple groups, because the idea is we understood all these ones that are simple. We've got the pieces of the puzzle, and we can do that. And there are these infinite family of groups called V-type and so various others. The alternating groups we will see, which we're going to talk about after the exam. The alternating groups are all simple, but they get big pretty fast. And there are these infinite families. There are exactly 26 random simple groups that don't fit any patterns. And of those random 26, and it's been proved that's an exhaustive list. There are no more. This is the big one. This is the largest simple group that doesn't fit the other patterns. And so that was kind of the interest there. The proof, the classification theorem was probably started in the 1960s, and it really wasn't completely topped off, I think, until the 2010s. I think they finally had to write up the last case. Everybody knew it was true for 20 years, but they were finishing up the thing. And the proof is seriously tens of thousands of pages long. So it's just spread out over a whole bunch of papers. It is you go absolutely mad trying to keep up with it.
So like that 10,000 pages, is that just like them printing out like a bunch of, or they?
No, that's like,
10,000
okay,
pages
this person did this case, and that appeared in some paper that's 100 pages over here. And this
Okay.
other person did this case, and you know, it's a nightmare. Okay, other questions?
For 20, working
Which fall was that?
2018,
2018. And which problem were we looking at?
40.
Okay, okay, so, I'm gonna go through it, if you don't mind, I'm gonna go.
Yeah.
So, here's the setup. We have, G is a group and H is a subgroup. Got some subgroup here, and show for all G and G, the order of H is the order of. Which question is this? This
I
is
think
number.
this is the wrong.
Did I do the wrong one? Which one?
Fall 2018, 40.
4B. Oh, maybe I'm looking at the, I got the wrong, here. Sorry. And there was, unfortunately, for me, a 4B on that one as well, so, okay, let's try it. Consider the group SA, find an element of maximal order in SA, and what is its order? Justify briefly. The justification in this one, I would give a lot of that.
Her days and give her feet. I don't know.
Right. So I'm gonna warm up on this one. What do you think, Peter?
Well, so maximum of this,
I agree. How do you go?
because you can separate into 5 and 3 else you use.
Right. If X and SN in X. These are disjoint cycles. You remember how we did that cycle multiplication? And we got these disjoint cycles. In the order of X is the least common multiple of order C1, order C2, order CK. So it's the least common multiple of the length of those cycles that you decompose it into, right? And so the question is, you've got 8 things to play with. 1 through 8. How do you make something that has the largest least common multiple of this, right?
I feel like there was a graduate problem. It was like this, but I don't remember if it was S8 or was that something.
I think it was S15 actually, so it was like a little bit more hardcore, I think. But in this one, so how do we go about this? Well, one candidate is can have a 5 cycle and a 3 cycle. And the cool thing about 5 and 3 is they're relatively prime, so the least common multiples are the product, right? And you can muck around this a little bit. 4 is not very good, right? Because the problem is it's 4 by 8. So you can get something order 15. And you can exhaust some cases, right? You could also certainly get an element of order 12, 4 cycle times 3 cycle. Certainly 15 beats that, right? You wouldn't want to use an 8 cycle because we've already beat 8, right? And you've used all of your elements. If you use a 7 cycle, you've got nothing else to use because there's only one number left. You'd have to make it 1 cycle. So you forget about that. What about a 6 cycle? Well, yeah, you've got element of order 6, and then you got another 2, but the least common multiple is 6, so you haven't helped yourself. So you get down to 5, and it's pretty easy to see this is the best you can do with 5. And when you get down into 4 and get the smaller cycles, once you're under that, the least common multiple is going to be at most 12, right? So everybody cool with that? So this is element of order 15, and that's as big as it gets. How many elements are there of this math? Okay. So let me rewrite this. A, B, C, D, E, F, G, H. How many? It's actually kind of surprisingly big. Was that?
The order matters, like I was thinking, oh, you just have this many foot.
Order matters, that's right. So how would, okay, so let me break things down first. Task 1, choose A, B, C, D, E. Because let me point out that when you make this element, you're using up all the numbers, right? You're using them all up. So once you choose who goes in the 5 cycle, maybe you know who's going over here. Everybody else over there. Nobody's left out. Right? So that makes this part of it a little bit easier. How many ways can we choose that? A, B, C, D, E.
Eight choices for the things.
You've got a set of 8 letters, and you're picking 5 to go here.
So 8 choose one.
I agree with that. 8 says it's like 56 cents.
So that's just keep that for the one.
Times 3 factorial. 8 factorial and 5 factorial and 3 factorial, both of them find that.
How do you agree with that? About that?
Was that
Actually, smart one, because I don't have that.
it's binomial coefficient.
Oh.
Yeah, it's the same thing as binomial coefficient.
For me to get down to 8.
How many of you have seen this before? But if you have, let me recall that in our notation, 0 factorial is all the time. How many of you have seen this? This is the binomial coefficient. It's the number of ways to pick a set of k things out of a teacher bigger set of big things, right? So here, what we're doing, just to pick these letters here, if I do 8 choose 5, I get 56, right? Notice it's symmetric. This is also 8 choose 3. I could have picked the FGH and told everybody else to go over the 5 side, right? And this is the same number, right? Which is, you can see the symmetry here, right? The 3 and 5. Okay, here we go. 56 ways to choose that. What's that in? Oh, what else? What else? What fresh deviltry do we have to deal with now? Well, suppose I pick 1, 2, 3, 4, 5. Right? What about this? That's not the same as this. So now I've got something different, right? Holy buckets of fish. How are we gonna figure this out? How can we count this?
Now we have to look at the number of ways to arrange ABC.
And let me give you a little hint. This is one thing that'll make your life a little confusing. What did I do? I did 4, 2, 1, 3, 5, right? This is if you got, for example, a 1, you can always assume it starts, right? So you can always anchor A at the front. Does that help choose how many we have? So if I pick A, B, C, D, and E, I can assume that A goes here. Because if it's not, I'll just cycle it like this, right? So if I've got my A, B, C, D, and E chosen, and A sits here, how many ways do I have? How many choices do I have? 4 factorial. 56 chooses the letter. 4 factorial chooses the arrangement here. And what about this? Got the same thing going on here. Times 2 factorial. Or the automatic whatever system. And this is 56 times 48.
Yes, sir.
What's that?
You actually have to multiply that out. Would you just?
No, that's good enough.
I'm too lazy.
But that's, you don't need that. In fact, in a certain sense, that's a better answer, because if you just write down some, 4-digit number, I don't know what orifice that came out of, but this, I sort of understand what happened, right?
I manually counted them all. And then wrote down.
Right. I think you'll have a hard time uploading your exam on time. Okay, other questions? Yes.
Can you go over the proof for the question term?
Do you want me to go through the whole thing again?
I mean, you can like.
So here's the idea behind it, Cauchy's. I think I can give you hopefully an abbreviated version.
Yeah, not like we'll just like get the gist.
So if your G is in, and E prime such that E minus N, then there exists X and D such that your of X. Now here's the idea, it's a group actions kind of thing. You consider the set all possible P2s of things in G with the following stipulation. The product, if you multiply all the coordinates, you have to get the identity of G. Right? Equivalently, and I make an observation. So you've got all these sets, P tuples, the product, and the rule is product of all the coordinates has to be the identity. Now, I will be a whole ding dong. I'm standing up here trying to tell you stuff about the empty set. So the first thing I'd like to know is this crap that I'm creating. Is it a thing or is it empty, right? What if there's nothing in there? Then I feel like a fool up there trying to prove theorems about it, right? But it isn't empty. Can you name a P tuple that's in there?
Yeah.
The identity across the board. That works for sure. So this is not empty. Because 1, 1, 1. Now, the next thing I want to do is I'm going to count the number of elements in S. And this is where I'm going to use this, because this actually tells us. The product of these things has to be the identity. Let me put one more thing for there. I can pick these with complete freedom. As long as I make that last one work, right? Just make this the inverse of whatever that other chunk. So that means for P minus 1 of the coordinates, I can do whatever I want. And the last coordinate, I'm forced. So that seems to me that means this is in P minus 1. Because the number of elements in G is n, so I've got n choices for all these. And that's it. Everybody okay with that? So, since P divides n, P divides the number of elements fast. So the number of elements in this is divisible by P, and that's very important later. Now, so I've got that collected. So let me tell you what I mean by that. So this be where I wave my hands at it a little bit, but I was a little bit, well, maybe not a whole lot, a little bit more careful in class. So if I have A1, A2, AP minus 1, AP in S, here's the way that the group acts. Zero does nothing. 1 does this. So it shifts it in 1. Right? 2 bar. Etc. Right. So basically, what Z mod P does is it acts by shifting, and the reason this works as an action is because what happens when I shift this P times? I'm back where I started, right? When I do P shifts, it's like doing 0 shifts, right? 1 puts that here, 2, right. P minus 1 puts this here, and then P puts it back here, right? Everybody okay with it?
So you're defining this group action, or it's like some like upside thing? Or you're just
No,
saying, okay,
I'm defining this group action. This is the way Z mod P acts. And notice that then it is a group action because zero leaves everything alone. And if I shift by I and then I shift by j, then when I do that, so if I take a sequence and I shifted I and then I shifted j, that's the same thing as shifting it I plus j, right? And so that's why it's a group action. Very simple. So this group action makes an equivalence relation. So we say A1, A2, AP is equivalent to X1, X2, X3 if X1, X2, X8 is a shift of A1, A2. So in other words, these two things contain the same thing, but it's shifted. So they're in the same order. It's just where you start as You okay with that? So think that, yeah, you can think of this as sort of going around the circle and it's just different places where you start. This is an equivalence relation because every one of these sequences of coordinates, they're equivalent to itself because that's a zero shift. And if I shift I to get this one, I'm shifting this one by negative I will get you back here. So it's symmetric. And it's transitive too, because if I shift, if two sequences are equivalent, then the second one is a shift of the first. And then the third one is a shift of the second. And so the third one has to be a bigger shift of the first, right? So this is an equivalence relation. I claim each equivalence class either one or no. Now, one, so let me kind of take through. Certainly there is a class that has no element. Right, because in fact, the equivalence class with one element in it are the ones that just fill all the same thing, right? All X's, right? When you do a shift, you can't tell the difference. Agree? And I guess it's clear that no equivalence class can have more than P elements because to be equivalent, they have to be a shift of one another. There's most P ways to do that, right? Why can't it be less? Well, suppose that there is a class with less. I did this carefully by modeling arithmetic class, but if you'll forgive me, what I'm going to do kind of simple example. Less than. So that means that but that must mean that there are two things that are alike somewhere. Because you have the way that you have P elements is they're all different, right? But you must be able to shift that and you get this back, right? So maybe you shift this to I, and you got X1 in I's place, right? Well, that means that X2 has to be in I plus 1's place and so forth. And it turns out that the only way this can happen, because P is prime, the only way if you just kind of iterate this, right, that means when you jump I, you get x1. But now, when you jump I, you get it again. You jump I and get it again. Since I is less than p, I is relative to prime p, you eventually cycle back to 1, which means that x I is equal to x1 for all I. Right? So if you have less than p elements, if you ever do a duplication here, then just follow that duplication. Jump I, jump another I, which means loop around, jump I, and you will get back to the original one, and what you get is all of these terms have to be x1. So if there's less than p elements in an equivalence class, there's only one. So this establishes this fact. You either have to have all p or just one in every equivalence class. Does that kind of make sense?
Yeah.
And now we've totally vanquished this in the following steps. Let P the equivalence classes with yeah. Right. And let's say W the equivalence classes with one.
The set of all equivalence classes?
What's that?
It's the set of all equivalence classes? Or like the n equivalence classes?
All. Yeah, it's a selection of all of them. And W is all the equivalence classes with one element. Right. So the number of elements in S is the number of elements in P plus the number of elements in W. Right. Now, we know that P divides S. And P has to divide this because every one of these equivalence classes in here has P elements in it. Right? And I guess this should be one of P times this because this is set all equivalence classes. Yeah, that's set. Every one of these has P in it. So this is divisible by P as well. And every equivalence class here has just one element. Now notice this equation must balance. So P divides the number of equivalence classes with one element in it. But there's at least one, right? So the number of equivalence classes with one element is divisible by P, right? That'd be a group of P, but it's at least one. And greater than or equal to 1. So the number of equivalence classes is greater than or equal to P. So there has to be some equivalence class that contains only one element that's not this, because P is bigger than 1. So there exists an equivalence class. It looks like this. So X is bigger than 1. Any questions? That is some foreshadowing, because we're going to see group actions acting on the groups themselves. It's going to get us a lot of really nifty results about group theory. So, yes.
You said you can balance out of, like, why is it not just the order? Like, how is the order of W not just zero?
Well, these are all integers in play here, right? So think of it this way: the order of S minus this little p times p. If I take this over to the other side, that's an integer on this side of the equation is divisible by p.
Oh, so
And
it's,
that's equal to this integer, so that has to be divisible by p.
so it's not just, like P minus P, which is
It's not just one.
like P minus P.
No.
Okay.
This is all I know is some integer that's divisible by p, and this is some other integer.
Oh, okay.
Yes,
Does that mean there's these P elements that have order P?
well,
Some
no,
multiple of
at
p.
least p minus one,
Oh. bigger
right?
than one.
Because you've got the one equivalence class right there, and if you think about it, look at, suppose x has order p. X squared, x cubed, x four, all the way up to x p minus one, all have order p. So there's your p minus one elements, and then you've also got that degenerate identity one as well. So yes, there have to be exactly there have to be at least p minus one elements.
But there have to be at least P elements that have order that divide.
Yes, that is correct. That's correct. Okay, other questions? Yes.
Would you, go through all? Oh, cause we're in 2019, question two.
Spring 2019. Question which?
Two.
Sure. Let me make sure I got this right. Let Q be a group and KN, be normal subgroups, show the K intersection is a normal subgroup. Is that right?
Yes.
Okay. So. This one, I think, you can try to follow our nose on it, let's see. We're assuming that both K and N are normal subgroups of G. Show. The intersection is also a normal subgroup, right? Okay, first of all, let me be super careful. Why do we know the K intersect N is a subgroup of G in the first place? That's right. So, if you have something in X, it's in K and N. X and Y, this is K, and of course, K intersect N is not empty because they both K and N can hang out. If you have X and Y both here, then X, Y inverse is in here and X, Y inverse is in here, and that's, but I would be okay. It's probably best to say something, but I would say, we know from class that the intersection of subgroups per group is subgroup. That's something we could do. I'd be okay with that. But the big thing I'm sure you're worried about is normality, right? Before anybody goes, is anybody leaving without asking the question they want to ask, or you good to go? Okay. Okay, so the normality is the big thing, right? So let's let X, E, A, intersect E. And G, G. Right? Note that G inverse XG is in K as K normal G. And G inverse XG is in N as N is normal G. Right. So what conclusion do we come to? G inverse XG is in K intersect. So K intersect N is normal. Makes sense? Yes.
Question.
Oh, this is kind of a fun one, which makes it probably the hardest one on it. Show that no group can be written as a union of two of its proper subgroups.
And that makes sense, like when you were showing Z12, like you can't express it as of like
Union.
yeah, sorry, the union. Oh,
Yeah. Actually, it's interesting because not less than 5 years ago, I would call research call it, kind of jot off on this trail. He was looking at groups of bits as union sub, and actually in general problems. Anyway, so here's the question. Show that no group union of proper subgroup. So that is, think of the problem. If H and K are strictly inside of G, then strictly inside G. And I'll tell you what, this right here, I don't expect this union to be anything other than a set. Right? In fact, that's what essentially the problem is here. Of course, let me point out that you could write G as a proper union of two subgroups if you said, okay, G is G union G, right? But that's cheating. That's why we said proper. Any ideas why this is true?
But you're saying it still stays a strict subgroup?
What's that?
You're saying that it's still a strict subgroup, as in it's not equivalent.
No, it's a strict subset. I should, I'll write that way so it's clear. In fact, this is, let's see, under the, yeah, this is almost never a group. In fact, H union K is going to be a subgroup. Only if K contains H or H contains K.
Oh,
Yeah, it's pretty strong.
Wait, why is that never,
Well, let's find that. And I wouldn't say never, but if, so no. So it's probably more illustrative by doing this way. Notice if K contained H, then K union H was H, which is strictly from A to G. Right? So say if H contains K, the union is now K, which is strictly G. So we can assume neither contains the other.
and we're saying contained as in like subgroup?
Right.
Okay.
So in other words, what we can assume is there exists an H, it's an H and not a K, and a K, it's a K and not H. So so how does this go? Okay, so let's suppose G is the union of H and K and see if we get confirmation. Anybody? Let's see. Was it? Very good. Consider the element HK. If H union K G, then HK is in H or HK is in K. Do I agree with that? If it's in the union, it's got to be in one of them. But if HK equals H prime and H, this implies that K equals H inverse H prime and H, which is a contradiction. Because K doesn't live in H. And symmetrically, if HK equals K prime in H, in K, that is, this implies H is equal to K prime, K inverse in K.
How is it a contradiction if like, is are we saying? Like, would that not just be like for all? Like, couldn't there be a K that is an H? How do we know that that's?
We selected these.
Oh, okay.
Yeah, these are specifically selected.
Oh,
So that H is an H but not in K. Because what we showed earlier is if H contains K or K contains H, then that union step doesn't work. So I said, okay, you can assume that either one of them contains each other. So there has to be an H here and a K here. H that's not in K and a K that's not in H. Because if this was, if there was no H that's not in K, then H is in K. If there's no K that's not in H, K is in H. So I selected those two elements, H that's in H but not K, K that's in K but not H, and I multiplied it. And I showed, okay, if that's the case, I've got a problem.
This is also.
In fact,
Did you show it to? Well,
uh,
here,
well, in
these
fact,
five-
I mean, so S3 even, which is not a billion, is the union of 4 proper subgroups. And for 3 of these examples I can think of, this is like that vector space thing, where you add things component wise, mod 2. This is 0, 0, 1, 0, union, 0, 0, 0, 1, union, 0, 0, 1, 1. So this one is the union of 3 subgroups.
So you have like finite to many generators. Using this subgroups.
Well, you can certainly do that. I mean, if you. Yeah, no, I mean, it could be more.
Like if you have a set that's generated.
So here's the problem. S3 is generated by a 3 cycle in any one of those 2 cycles you pick. But if you look at the union of those 2 groups, you don't get it.
Because there's inter.
Because the union is just a set, remember? I mean, the union, so the intersection of a collection of groups. So if you have a collection of subgroups of some group G, the intersection, that's always the same. Unions almost never. Almost never.
question about, like order of an element.
Uh-huh.
So if we're talking about order, like A has to be cyclic then? Or like if A to the n equals the identity, A is cyclic, right? Because then it has to.
So if A, so the order of A and G. If it exists, and if no such n exists, we'll say it's infinite order, but I will focus on it. The order of A is equal to the order of the subgroup of G generated by A. Because if we look at the subgroup generated by A, well, you've got 1, A squared, A cubed, and A n goes back to 1. goes on a vicious little circle. So it's the order of some generator. So particular order of an element. So the connection with order of the group is the order of an element is the size of the cyclic subgroup generated by that element.
Okay, so, wait, would G have to be cyclic then for an element to have an order?
Anything. So for example, but you remember that Rubik's Cube thing that I did over and over again and came back, right? The Rubik's Cube is not a cyclic group, right? I mean, it's not even a billion, it's a big mess. But if I took that one element that I went X, Y, I would call that A. I had to do that 105 times before it came back. So that little element generates a little subgroup for 105 inside the Rubik's.
So the element itself is.
Any element of group.
generated.
Yeah, that's right. You can take any group anywhere, pick out an element and say, hey, generate a cyclic group for me and let it go. And it'll generate a little cyclic group.
Okay,
And that cyclic group may be infinite. But if it's finite order, it'll be a little finite thing that comes back to the identity.
Okay.
Then it's just gonna be a cyclic, right?
That is correct.
Yeah.
And the generator, the additive generator one has infinite order because you never get back to two. That's why in general, when I say, when you use generators and generators to generate it, I say, not only do you use the letters like you said, the group generated by X, Y, and Z, but you use their inverses, right? When the element has finite order, you don't need to worry about that because it generates its own inverse, right? But if you have something like one in the integers, you can't add one to itself and get -1, so you gotta throw in the inverses as well. Okay. Other questions?
You recommend, Karen?
I'm not staying up very late on Thursday. I think that's a classic mistake. So I think you should be well rested.
So, like tonight.
Yeah, that's right. If you're gonna do that crap, do it tonight. Yeah, that's right.
I have 2 exams tomorrow.
Is what I would say, like, here.
Well, so you stayed up late Tuesday for them,
Yeah,
right?
yeah, for sure, that is, would you recommend doing like practice exams and with the time constraint or?
If you're worried about your time, yeah, I mean, that's not gonna hurt. I think there's enough exams for you for everyone to, see how fast. you can go. Make sure that you get the definitions, right? I think that don't focus so much on doing proofs. I mean, if you've been doing the homework, then that's gonna help you out a lot, right? As far as being ready for that. Just make sure that you're pretty slow for those definitions, right?
Go over those like 3 different groups. And the center, the centralizer.
Oh, yeah, so there's the normalizer, the centralizer, the center was a special case, so, I think, she's approved. And I want to have some non-inclusive. Then normalize routine, and this is probably familiar now, this is the set of G and G such that G inverse A G by A. And the centralizer in G of A is a set of E and G such that G A, say G for all A. So it's a set of everything that commutes with anything. And the center of G is actually the centralizer in G of G, which is a set of G and G such that GX equals X and G for all in G. What's that? Yes, this is normal always. Yeah, center's always normal.
So with the centralizer is the normalizer of an element,
The
or would it be the other way?
no, so let me see if I can. Yeah. Big example. Um, Okay. Good. I'm gonna make A active up to subset. So three. So the normalizer. in G. Let me see if I can- You're welcome. This is the set of every G. Such that G inverse AG. A. And in this case, this is all G here. Let me kind of demonstrate. And the reason that I know this is because this group is normal, right? It's of index two. It's normal. So when I take when I conjugate everything, any conjugate of this group is this group back, right? So if I do this is
Index two implies normal, but normal doesn't imply index two.
normal is not.
Okay, that was
Wait.
confusing me for a minute.
What was that?
The
What we
index
proved in the
equals-
homework is if you have a subgroup of index two, it's normal. But if it's normal, it doesn't mean it's index two. There are plenty of normal subgroups.
Okay.
are index. One goes. Pretty good. You okay with that? So the normalizer of A is all this afterward, equalizer in G. But this is the set G such that GA is a G for all A. And this is A. Right, because notice that when you take two elements of A and multiply, the order doesn't matter here, right? This times this is this times this is the identity, this times this is this, right? You okay with that? So it's at least A, but none of the little two cycles are in this, because here's the problem. If you look at, for example, 1, 2 of 1, 2, 3, this is, what the heck is it? It's 1 goes to 1, 2 goes to 3, 3 goes to 2, right? On the other hand, if you reverse the order, this is. So here the centralizer, or I'm sorry, the normalizer of this is the whole thing, right? Because it preserves the entire set. But here, it preserves, even though the set's preserved, it's not true, because another way to write this is A equals G inverse AG. So what happens here is when you do G inverse AG, it leaves everything alone. This leaves the set alone, which means it could have pushed the elements around inside the set without fixing them all, right?
Okay.
And that's the difference.
So how is that equal to A if like 1, 2, or if 2, 3 is not an element?
Well, so it violates this. So what that means is 1, 2 is not in the central answer, right? Because
Oh,
1, 2
okay.
times this gives you a different result
Okay.
than this.
So it's G that's the element of it and, okay,
That's
yeah.
right.
Okay.
Let me also, this is also a point of confusion. This is the set of elements that commute with everything in A. That doesn't even mean the elements G and the centralizer have to commute with each other. They just have to commute with A. Right? So I might have G1 and G2 in here that don't commute, but both of them commute with A.
And then it's always true that if like a set is normal, then the normalizer of the set is the whole set, or it's G is a whole group.
Okay, so so if. H is normal in G, then. Normalizer in G if that subgroup H is all of G.
Okay.
And the other direction works too. If you have a subgroup, and the normalizer of that subgroup is all of G, then that means that subgroup is normal.
Okay. And yes. But, the theorem where it's like N is a normal subgroup of G, if and only if, N equals the kernel of D,
Of some homomorphism, yeah.
would that be like, so the homomorphism is, no, wait. Which one is either me?
So I can go through it. This, so let's make this way to see it. No. Um. There are potentially many homomorphisms that have the same kernel. Right, so for example, if you look at, I'll give you a good example. If you look at all the automorphisms of Z2, remember those matrices that we have, the 6 of them? It's isomorphic S6. Every one of those automorphisms has 0 kernel, but they're all different. Right, so just because. So if I tell you that you have a homomorphism from G to H, and I tell you the kernel is in, that does not give you enough information in general to tell what the homomorphism is.
Okay.
Right, but, so if, number one, kernel phi is normal. Doing it over there. Show you that.
It's just because it's good, 7, or it's everything that takes its big.
Right, so kernel phi is the set of x and g such that phi x is nothing to be right. I'm gonna prove that this is normal. So. What I need to show is G inverse X. So look at. G. Now, this is E G inverse E of X. E. Agree? That's me liberal with using homomorphism. So, what can I do now? What might be my next move? It's chess game. What are you about for the best?
It's like, and
That's right. It's in the kernel phi, so this is.
get rid of it.
So this collapses down. And what did we deduce? Well, what we figured out here is that. Oh, right, G inverse and G seems to. So I've got X and the kernel feed, and then conjugates in kernel feed one. Okay, so far? Now, I think really what you were talking about, or emphasizing perhaps, is the other direction, so now suppose. Yeah. Is a normal subgroup of G, and the theorem that I think that you're talking about is this one that says, okay, if I walk up to you on the street, give you a normal subgroup, it's the kernel of some homomorphism. Well, this is, I feel icky doing this, it's almost cheating, but here's the homomorphism. We'll call it homomorphism. And G minus N. And the way the homomorphism works is of little g is the coset GM. This is pretty easy to see is a homomorphism because if you look at pi of xy, this is xy n, which is x n y n, because n is normal, and this is the way the multiplication works, which is pi of x y. So it's a homomorphism. Not only that, it's onto, but I don't care that much about that. And the kernel is the set of G and G, such that the coset Gn is the identity coset, which is the set of G and G, such that G is in N, which is N. So there you go. The kernel of that. Let's call it the quotient map, projection map. That's got kernel in, and there you go. So it's almost like a cheat because of the fact it's a normal subgroup. G mod n is a group, and I just made that homomorphism.
Okay, and then, but when we're making homomorphisms, how do we like show that it's well defined, or is that like showing it's
You don't need
homomorphism?
to, right? Because when you're talking about if something's well defined, you're talking about if something's a function. So input G, this has got one and one, only one output. The input is G, and the output is this coset.
Oh, okay.
Like, there's no ambiguity on your input. My domain is just elements of G. Now, if this had been a collection of cosets, or we might be picking different representatives, that's more problematic.
Okay, so the fact that like you defined it like that, it's obvious that it goes to. the
Right, this is a function, because given any input, there's unique output.
Okay.
Other questions? Everybody stared into that. Oh, Wes, we were like at the OK Corral or something.
I have a question on the homework
Okay, sure.
for 3A. I'm just a little stuck. I think it's helpful. Yeah. Oh, the order of age divides.
Okay.
Okay.
Oh, yeah, so choose a finite group and n is normal. G.
Yes.
I think if you can overcome here, I think the A is going to be big. I think B once. Okay, so we have H is a subgroup of G. Greatest common divisor. However big H is, and of course G is fine, so all the subgroups are fine. And the index of N and G is equal to 1. And what you want to do is show that H is a subgroup of N, right? So really, all you gotta do is show H. Do you make any progress?
The only thing I managed to show is that the order of H divides the order of H, which doesn't.
How did you show that? I mean, it's something gonna be true.
I mean, yeah, it needs to be true, but it doesn't necessarily apply. I don't. So, true. It's just a lot of finagle,
Oh.
but
Let me take a look here. So did you mess around with like indices and so forth?
yeah, I really just, it's a lot.
Hey, that's not.
It
Yeah.
does what?
Oh, no, it's not. Oh, okay. Okay. So this is actually an important piece of it. I'll go ahead and put my foot on it. So. HN is a subgroup. Why?
Because. Yeah, kind of so HN, because N is normal and H is a subgroup.
Right, H is a subgroup and N is a normal subgroup, and that's more than enough what you need for this.
For N being normal, like, does it matter that N is normal, or like, if N is just a subgroup in general, would H
No,
be?
no, if it was just a subgroup, you got no idea about HN. You need that condition about H is contained in the normal, that sort of thing.
Cause, well, why wouldn't like HN, like if HN or little HN is an element of HN, like the
Right.
group, why is that not, like, since little HN is in G, like, how is that not a subgroup?
Can you rewrite this? This? It might not
Oh.
even be close,
Okay,
and that's why you need normality, because you need to conjugate around.
okay,
That's essentially it. That's really the problem. A lot of people have problems with that commutator problem. That's because a lot of people assume that the commutator subgroup only consists of commutators. And that's not true. It's true that the inverse and a conjugate of commutators are commutators. But in general, if you multiply two commutators together, there's no guarantee it's still a commutator. Sometimes it is, but not always. Let's see. Right. This is a subgroup of two, and it contains N. You remember that? In fact, all I have to do is take the identity and it's got all the elements in it. Now, if you look. Let me also point out, what is the second isomorphism? Say isomorphism. Right, and what is, do you remember this one? Isomorphism. H modulo the intersection, right? Now, these two groups are isomorphic, so. Because they're isomorphic, in fact, they're both finite, because G is finite, so all these little players are finite. What is the word of this? it's the index, right? Same. So. Let me point out that. Important age. Equal to. Actually, I meant to say, but. Let me do it this way. Follow it. And this is just the order of H intersect in. And. Let me how that helps. What do you know about these two numbers? What do you know about these two numbers?
Oh, yeah,
They're coprime. So their divisors are all relative. Here, I got you. They're relatively prime. So when you divide for that. So would you agree? Right, because this is a divisor of this, and this is a divisor of this, and they have no factors in common. One. I agree with that. So I had the greatest common divisor of D and D, because these two orders are the same thing, is 1. Now pray tell, if I have two positive integers, D and D, and the greatest common divisor of D in itself is 1, what does D have to be?
1.
1. So D, which is the index, the index of H intersect N at H is 1. So what does that mean? There's only one coset of H intersect H. So and if H intersect N is all of H, what does that mean? It has to be contained inside of there. Does that make sense? Yeah. So it's a little bit convoluted. There it is. That's one.
That's whatever it says.
earlier sentence. And it's contained in H.
Right. So what you're saying is when you intersect N with H, you get H. So that means that H is contained in N.
Oh, okay. Oh. When this one, there's one other thing to like just cancel them out is H and divided by n is just H? Is that what
No.
you said? Oh,
It's H mod, the intersection, that's the problem.
oh,
The
okay.
overlap's the problem. Gotta crush that.
Oh, okay.
Any questions? Okay. Others.
How do we know that H is, well, is it because what's it called? There's only one left coset that H is a subgroup. Like, how do we know that it's not just a subset? Oh, because H itself is a group. Never mind.
Yep. Anything else? Alright.
How's he trying?